So guys, the big idea here that we're going through in this unit, and this is going to be a fast unit just like the last one, is balancing equations. I think that we're going to spend about a week on this. Okay. The entire unit is based off of one idea called the law of conservation of mass. I think we've talked about this one before, right? When we talk about history of the atom, you guys ran across a guy who said that when we had a chemical reaction, that the amount of matter that you started out with is the same as the amount of matter that you end with. So the basic idea is that in any reaction, no matter whether it's a chemical or a physical reaction, you can't create or destroy matter. So a chemical reaction, by definition, is when atoms regroup to form new substances. What this means is that bonds have to be broken, chemical bonds have to be broken, and or new bonds have to wind up forming. So both of those things can happen. I'm going to actually modify the definition that's on this slide real quick here, because a chemical reaction doesn't require that bonds be broken. It requires that bonds be either created or destroyed. Quite often both things happen. Every once in a while you only see one of those things happening. Usually it's just that new bonds form. Chemical equations are a little bit different. They're written out. They use the chemical symbols. So the whole reason why we spent some time doing nomenclature, doing naming and writing formulas, is because we have to be able to write out chemical equations. We're going to write out the chemical formulas to show what happens during a chemical reaction. There we go. Moving forward. There are 4 signs I need you guys to know. Put stars next to these. 4 signs I need you guys to know that will occur when a chemical reaction occurs. Now, what I just said might be a bit of a misnomer. These things don't necessarily have to indicate a chemical reaction, but they're pretty gosh darn good predictors. Okay. So one thing is a color change. You can see there in that nice little picture we've got, a blue liquid is being poured into another Erlenmeyer flask, and it appears to be changing color. So that is an indication of a chemical reaction. Okay, when you have a color change that you're not exactly expecting. And when you put red Kool-Aid powder in water and the water turns red, is that a chemical reaction? No. Okay, you're expecting it to turn red. Okay, but unexpected color changes often are signs of a chemical reaction. Another is temperature change. And I'm going to modify this slightly again. Where is my little mousey? Here it is. This could be also energy change. Okay, there are some chemical reactions that don't give off heat but give off light. And those are good indications that a chemical reaction is going on too. We don't have many fireflies left because of the frost, but the glowing of a firefly's butt definitely is no temperature change, but you give off light. There's a chemical change going on in there. The things that happen, formation of gas. Okay. Sometimes if you got something in solution, you might be seeing bubbles, or if you don't have a solution, you might be seeing smoke come off or a haze come off of a reaction. And then finally, the 4th sign of a chemical reaction is that we've got a precipitate. And precipitate is a fancy word for solid. There we go. So here's a basic primer on how to read chemical reactions. What we've got here is we've got 2mgs plus O2G. Then we've got some arrow, and we get 2MgO with an S. What's going on here is that, yeah, there we go. These subscripts stand for the states of matter. Okay, so S stands for solid, G stands for gas. Okay, obviously the chemical symbols are telling us what elements we need to, what chemicals we need here. Mg is an element. Oxygen is one of our diatomic elements. And this guy over here, MgO, we would call magnesium oxide, right? Aubrey? So we need a 2 here because oxygen is diatomic. Never comes by itself. 2 atoms of oxygen always have to be attached to each other. Magnesium, on the other hand, is not diatomic. Okay, so I can't write Mg2 with a subscript because that would imply that magnesium is diatomic, and it's not. Magnesium doesn't bond to magnesium. It doesn't always come in 2s. So what we do is we use coefficients. And if I can get this thing to write properly, coefficients, I-E-N-T. Yeah, I didn't spell that right. Okay. So we use these things called coefficients, and that tells us how many we need to use when we don't have diatomics. So what this is telling me is that I have 2 atoms of magnesium, 1 molecule of oxygen, and I'm going to wind up with 2 formula units of my magnesium oxide. I think if you guys remember, in the last unit I said that we don't call ionic compounds molecules. We call them formula units instead, so this is where we're going to start using that vocabulary. So at the top half here, it does say 2 atoms of magnesium plus 1 molecule of oxygen makes 2 formula units of magnesium oxide, which is the smallest possible reaction that we can have. But the problem is that we can't count out atoms, can we? There's no good way to count out atoms or molecules or formula units, so that I just have 2 atoms in 1 molecule and 2 formula units. So what these ratios actually wind up talking about, we use the mole to measure out similar proportions. So 2 moles of magnesium would be a proportion of 2 atoms of magnesium. It would be an equal proportion. Okay. 1 mole of oxygen would be an equal proportion to 1 molecule of oxygen. And 2 moles of magnesium oxide would be an equal proportion to 2 formula units. Okay. It turns out that 1 mole is, and we talked about this before, right? I think I kind of alluded to this. 1 mole is 6.022 times 10 to the 23rd pieces. I'm going to use the word pieces here because it can be atoms, it can be molecules, or it could be formula units that we're trying to count out. And it's just a lot easier to measure out a mole's worth of stuff than to try and measure out 2 atoms worth or a molecule. Okay. So here's, oops, where'd it go? There it is. Here's the basic idea. The arrow tells you that a reaction is happening. Okay. And I usually abbreviate reaction with an RX. When you go to the druggist and you get, when you go to the pharmacist and you get prescriptions, sorry, I was using the British term for a moment there. When you go to the pharmacist and you get prescriptions, prescriptions are written as an RX, right? Because they're things that you take that want to react with your body. Okay. The arrow separates two sides of the equation. Products are always written on the left side. Oopsie, I did that wrong. Hold on. I don't know why I like to say products first. Products are always written on the right side, because there are things that are being produced. Whereas reactants are always written on the left side because they're the things that are actually doing the reacting. When you're writing a chemical equation, reactants are on the left side. They're the starting substances. Do we need that information written down? We kind of have that in a graphic, right? Okay. Products are the finished product. They're always on the right side of the arrow. Plus signs in between things means that things are being reacted to or being added to. It depends on which side of the reaction you're on. If you're on the left side of the reaction, things are being reacted with each other. Okay. It is possible to have an arrow that is double-headed. Okay. Some reactions only go one way, and the arrow indicates the direction that they go. Some reactions are reversible and can go backwards. And so when we get reversible reactions, we draw double-headed arrows. I think your textbook winds up showing double-headed arrows looking like this rather than like this one over here. But basically, those arrows mean produces, yields, makes, creates. Most of this is stuff we've already talked about. Coefficients are numbers written in front of a formula to indicate the number of particles. Again, that word particles is in quotes there because it could mean atoms, it could mean molecules, it could mean formula units. Okay. Like I said, I think we've taken most of this in already, so I don't think you need to write this slide down. But the information here is that between these two slides is that subscripts and coefficients wind up giving different bits of information. So for instance here, there's a subscript, bless you, there's a subscript on H2O. And the 2 is giving us information about how many hydrogens we've got. So when we take a look at the drawing over here, there's a hydrogen there, and there's a hydrogen there. Okay. The fact that there's not a subscript on the O means that we're assuming there's 1. So there's my 1O. Okay. So the subscripts are telling me information about how many things make up this molecule, or how many things make up this formula unit. Whereas if I put a coefficient in front, what that's telling me is how many of these molecules I have in total. Now I could take this 2 and say, hey, I have 2 times 2 hydrogens. I should have 4 hydrogens in total here. And I could take this 2 and put it in here and talk about the oxygen. I could say, okay, there are 2 oxygens. Well, basically what I'm doing here is multiplying. 2 times 2 is 4. 2 times the 1 is 2. So I should be able to find 1, 2 oxygens, and 1, 2, 3, 4 hydrogens. All right, so when balancing chemical reactions, the whole reason why we're balancing is because of that first slide we talked about, Lavoisier, the law of conservation of matter. Okay, there has to be the same amount of stuff on the left side as there is on the right side. You can't create or destroy matter in a reaction. Well, you can, but that's called nuclear chemistry, and we're not going to do nuclear chemistry. Okay. Here's the basic idea on how I usually like to work this out. Okay. What the law of conservation of matter says is that the amount of hydrogens on the left side of the reaction have to be the same as the amount of hydrogens on the right side of the reaction. Okay. Same thing with oxygens. The number of oxygen atoms on the left side have to be the same as the right side. Usually what I like to do is this. I usually like to start with the first element, write it down below the arrow. Okay. Second element, I write it down below the arrow. Okay. And I just use this to keep a tally of how many atoms are on each side of the reaction. So for instance, it looks like on the left side of the reaction I've got 2 hydrogens. And it looks like for oxygens I've got 2 also. On the right side of the reaction it looks like I've got 2 hydrogens. And it looks like the number of oxygens is 1. Now, does this reaction, the way it is, look like it's obeying the law of conservation of matter? No, there's not enough oxygens on the right side. We can't just simply go in there and toss a 2 in there, right? That completely changes what that substance is. That's no longer water, that's now hydrogen peroxide. So we can't do that. Let me get the eraser out. That's not something we want to drink. Okay. So the way that we do balance an equation is simply by changing coefficients. Sometimes that means we have to change more than 1. I need more oxygens on the right-hand side of the reaction, so what I'm going to do is I'm going to write a coefficient 2 in front of water. What that's going to do is that's going to double my amount of oxygen, so I'm now going to have 2, but what else did it do? Right? Right. I now have double the hydrogens. Okay, so now I've got 4 hydrogens. Can I fix this easily? Sure. We look at the left side of the reaction, hydrogens by itself. I want a total of 4 hydrogens on the left side. What coefficient do I need to use? Right, 2 times 2 gives me 4. What I should say here is this. What's understood about my number of oxygens? There's 2 atoms in a molecule. What coefficient is understood to be here? Yeah, it's understood to be a 1. Do you guys have to write the 1s in? No. Okay. What you're going to see on my answer keys is I'm going to write 1s. Okay. Because if we want to discuss the coefficients for this, I'm going to say that it's 2, 1, 2. Okay. And another reason why I write the 1s in is because I get interrupted as I'm balancing equations. And if I leave blank spots, I won't know whether I finished it or not. You know. So I write the 1s in just because I get interrupted a lot. Ooh, this is a fun one. A bit longer. I'll let you guys write that down. Okay, so if I'm working this out again, pretty much a matter of using the center here, the arrow, to write down the elements that we've got. I usually start on the reactant side, and I just list all of the elements as I come along to them. What do you notice here? As I'm going along, I see that I've got another hydrogen. Do I have to write hydrogen again? No. Okay, so I just want hydrogen. And basically, if you go through all the reactants on the left side, you should have all the product elements on the right side. If anything changed, there's a new element on the product side, then that means that there's a typo. Okay. So for hydrogen here, how many hydrogens do we see in total on the left side of the reaction? I got to be careful here. There's 1 over here in the HCl. And there's 2 in the calcium hydroxide, the way it's written. How many chlorines? Calciums? And oxygens. Right? Okay, hydrogens on the right side. Yeah, there's 2 in the water over here. How many chlorines? How many calciums? And oxygens? Looks like just 1 over here in the water. Okay, is it balanced the way it's written? No, so we're going to have to do some stuff. Now, guys, there's not wrong ways to do this, but there are some helpful tips. Oxygen is usually devious. Okay, you usually don't want to try and start with oxygen. You want to try and end with oxygen. So if I say, where do we want to start? We could start with the chlorines or the calciums, but I wouldn't start with oxygen. Okay, where do we want to start? All right, somebody's, hydrogen? Okay, hydrogens are done, right? 2 and 2, we're done. Don't need to worry about hydrogen. Really? Did I write it down wrong? Oh, shoot, I said 3 and I wrote 2. All right, let me change that. Thank you. All right, so we want to try and do the hydrogens first, huh? That could be tricky, right? All right, we could just let's take a look at the hydrogens real quick. Hydrogens come in pairs on the left side. One of the formulas on the right side, they come in pairs, right? H2O. Okay. On the left side, one of them, they have to come in pairs. But in the other one, they have to come as singles. What's causing me the most trouble, the singles or the pairs? The singles, right? If I change this one so that it is forced to come as an even number, that should help me get hydrogen to balance out. Okay, so if I've got an even-odd problem, I can look at it and go, okay, well, how do I make one side always be even? If I always put coefficients that are even in front of HCl, hydrogen is forced to always be even. Right. Ooh, that changed chlorine on the left side. And it should have also changed water on the right side, right? Let's see, you got twice as much water. Oh, hey, check that out. We didn't even try, and it's fixed. Right. We can double check things. 2 hydrogens plus 2 hydrogens is 4. 2 chlorines is 2. A calcium and oxygens, there's 2 up there. Calcium, let's see, hydrogens here, there's 4. Chlorines on this side, there's 2. Calciums, it looks like there's just the one, and oxygens, it looks like there's two. Give you this one more example. Should I give you the hint first or after? After? Okay. I'll give you the hint after. Go ahead and try this one out. So here's a tip. Anyhow, you probably just tried to do this with silver, nitrogen, oxygen, and carbon separately. How many of you guys tried that out of curiosity? Okay. Right. How many of you guys did it the way I just wrote it down here? Silver, nitrate, and copper. Check this out. I think it's a little bit faster. If you see a polyatomic ion exactly alike on both sides, you can count it rather than counting the components to it separately, the elements. Okay. So I've got one silver, one nitrate, and a copper all on the left side here. On the right side, I've got a silver, a copper, and two nitrates. Okay, this should make balancing it a little quicker, because I should be able to come over here and go, hey, I need two nitrates. So I'm going to put two coefficient there. That changes my nitrates. It changes my silver. Okay. This is pretty simple now. Silver is the only thing that needs to be fixed. I'm going to toss a 2 out here. And pretty much that's it. We can check it, but it's going to wind up being right.